The derivative of a function with more than one variable will not really be well defined because there's more than one variable that we take the derivative with respect to. So we can take the derivative of some function with respect to one of the variables, and that is why it's called a partial derivative. It's because it's only one variable at a time. So let's take a look at the old rate of change from calculus, where we took the derivative of a function of one variable. And if you remember the notation that we tried to establish last week, these are functions going from R to R, set of real numbers to the set of real numbers, where we only have one variable for the input. And with the one variable for the input, that's the only variable we're dealing with. And so the derivative is written in several ways. dy dx use the prime notation, df dx. So there's a lot of ways to write our derivatives, and if you go into physics, you can use a dot notation, y dot. We're not going to do that. But it really boils down to, by definition, this is the limit as h. We usually call it h. Sometimes we call it delta x. Say h goes to 0 of the difference quotient, and in the difference quotient we kind of create a secant line, and as h goes to 0 it becomes a tangent line, or the slope of the secant line, and as h goes to 0 it becomes a tangent line. Note,
the secant line is what's passing through a point, right?
It's passing through a couple of points in the graph.
And then as it approaches 0 from both sides, it ends up only passing through.
Being a tangent line, yeah. So we could think about it as an x and x plus h, and then this is the length of h. H is a distance, and as h goes to 0, the secant line becomes more like a tangent line. And the slopes is what we're looking at. The slopes are what we're looking at. So this is a definition of the derivative for one variable. It's a limit. So with two variables, let's try to think ahead before I write the formula down or before I copy the formula. So in two variables, we have two variables that we usually represent as x and y, but remember, they could be anything. They could be s and t, u and v, or whatever, any pair of letters that you can think about. And then the output variable also could change. We have z, but it could be T, capital W, C, whatever. But the point is that we have two variables now that we have to choose from. And so when we want to take the derivative of z, we will have a choice of what derivative to take it with respect to, because there's two variables that we're doing. So if we take the derivative of something with respect to one of the variables, what do you think is going to happen to the other variable? You treat it like it's a constant. Okay? So that's how we're going to deal with partial derivatives.
So if we're treating, like, let's say it was like y to the 7 plus xy, if we're holding y as a constant, y to the 7 could also be a constant, right? So if we took the derivative, that would just be 0?
Yep.
Okay.
Yeah, so if you have y by itself as a constant, just pretend it's 5 to the third power. 5 to the second or third power is going to be 0. So those things will disappear. Yeah? Well, if x and y are dependent on each other, then they wouldn't necessarily, they may not fall under this category of a function of two variables, because then, yeah, you could still treat it like they're independent of each other. And then if you throw in that third dependence relationship, then your things will end up changing. In fact, we might do some of that stuff. But let's take our time first with the definition. So who'd have known that by adding another variable, we super complicate things from the definition to the notation? It's not really that much more complicated. We are just looking for two components, right, for your input, and then a slight change in the two components. So here is the formal definition of a partial derivative, and this is a new notation, f sub x and f sub y. The subscript, whatever variable is in the subscript, will tell you what you're taking the derivative with respect to. And this is probably the easiest notation to write, because all you have to do is a little subscript, instead of the Leibniz notation where you have a fraction, d something over d something. Not only that, your d's change.
Curly.
Yeah, it's curly. It's called a partial d. It's not a particular Greek letter. It's just they needed another d from somewhere, and so they decided, instead of writing delta, because delta is used for other things, they use a partial d. Now, I need you to be able to write your d's differently, because a straight regular d will mean something different from a partial d. So this is delta that we're not going to use. I mean, it might be used for other things. Lowercase delta. I suppose if we're going to bring that up, this is uppercase delta. And delta is usually the symbol for the change in something. And this is your partial notation. So we actually say partial. And this is your d. What? Should I put d? No. I don't know. That doesn't look right. That's your regular d. So a simple fx or f sub x will suffice for, and make sure it's a subscript, f sub x. This is written, you know, when you guys were learning how to write your letters. So this is f sub x, right? Not fx, because that's an O short of a fox, whatever that means. But we want to make sure that you write your subscripts as subscripts, superscripts as superscripts, and this is a subscript, so f sub x.
I guess this is where we have to get really good at WebAssign at knowing the subscript and superscript buttons in the function.
Yeah, I think a lot of times that you're going to be inputting functions, but whenever and they might, whenever WebAssign asks you to write down the symbols for it, if you want to write it as a subscript, make sure you
Like when we had to do
shift underscore would probably do it, yeah.
and B and like B naught would be like B and subscript.
Oh, okay, yeah. So good. There's some flexibility. Now, there are cases where we have a function of 5 variables, and anything past 3, we got x, y, z, and then we kind of run out of letters at the end of the alphabet. So sometimes they start using numbers to denote your first independent variable, your second independent variable, your third independent variable, etc., to get to your whatever variable that you're dealing with. So that's sometimes used as a notation. We in this class won't be dealing too much with functions of more than 3 variables, so we probably won't be using the number notation. But it does exist, just to let you know. Also, the capital D is another common notation to say derivative. This is your derivative, and if you put a subscript, then it's a derivative with respect to whatever variable you're dealing with. Mathematica uses a capital D.
So the one is just that derivative of that variable one?
Yeah, so the first variable.
Okay.
And because your input here for R, for your function f going from R2 to R, your input is an ordered pair, and the order of the pair that you're putting in makes a difference. So the first variable would denote the first variable. Okay. So let's take a closer look at this and see a picture. Do pictures help? Pictures always help. Okay. Unless they don't? What?
I've seen some bad pictures before.
Yeah. Well, then I hope this will help. I want to introduce you to my generic function. Z is equal to f of xy. Calculus teacher, when they want to write a generic function, they draw a generic function y is equal to f of x. They just do a wavy function. Well, this is my generic 3-dimensional function. Okay, this can represent your hyperbolic paraboloid, your cone, your whatever function that we're dealing with. This is my generic function. And you'll see this a lot, because it's pretty easy to draw, and it's a good representation, a decent representation of nice, smooth function. And what we could do is I can make relationships between what's happening on the xy plane, which is our domain. Our domain is in R2. And then the output is your z-axis. And this is our representation. So if I put a point on the xy plane, then we can say that this is a 2-dimensional point, but you can throw it in 3 dimension by putting a 0 in the third component. So let me just take a quick look here. It just says x and y. So I'm going to call it AB. We call it AB, x naught, y naught. Let's call it AB. So we can denote this point as a two-dimensional point, or we can actually denote it as a three-dimensional point. By just saying it's on the xy plane, and you say it's on the xy plane by saying the z components equal to 0. And this has a corresponding point that's on the surface. Now the surface has infinitely many points defined by things that are happening on the xy plane, its domain. But this special point over here, right above AB, is an actual point that I can denote by something. So AB is your x and y components, because it's directly above it, right? And then the z component would be the z value if you put the AB into the function. So remember that f of AB is an output of the function. Some people just call it c, so that your point's ABC, but calling it f of AB is more informative. All right, let's throw our analogy back to our simple generic function y equals f of x back in 2 dimensions or back in pre-calculus. Here our points are just A. And then when you put this, you get A comma f of A, where f of A is the y value after putting A back into the function. Right? So this is our analogy. This is what we're seeing. All right. Now let's imagine that we're interested in taking the derivative with respect to, I think the better angle here to take the derivative with respect to is y. So let's take the derivative with respect to y. So let's focus on this idea of what f sub y is equal to, or you want to practice your partial notation. So I'm going to change the x's and y's and stuff, and I'm also interested in evaluating this at AB. So let me, sorry, I need to include some stuff here. Oops. You guys taking notes in pencil? I'm just going to insert that we want to evaluate this at AB. Don't you wish you could just move your notes like that? Like if you take notes in like on the computer and the OneNote program. Is that what you got? Charlie's got it going on. According to the definition of the derivative, this is a limit. Limit is some h value goes to 0, and we'll draw the h values here in a few minutes. F of x, comma, so x by itself is fixed. We're fixing the x component. And then the y, I'm sorry, I'm going to change that x also into an a. Can I? Yeah, I could change that into an a. And then b plus h minus f of a comma b divided by h. All right, let's go back to the picture and try to identify what's happening here. So let me label my x is equal to a, my y is equal to b at that point. So it looks like my x will remain fixed. So my x will remain fixed. I'll be focused on this line segment over here. X is equal to a. Now I'm going to look at my b and then add an h to it. So then I would have moved over here a little bit. So this is my new point a comma b plus h. Now if I pick up that point and put it into the f function, I would be somewhere over here. F of a comma b plus h comma the z value, which is putting this two-dimensional xy point into the function f of a comma b plus h. And remember that h is this distance over here. So what I've eventually found is the slope of this line segment by holding x fixed at a Now, if I take h and let it get closer and closer to 0, what I would eventually get is the slope of that line that's tangent to the surface at that point going in the direction of h, or going in the direction of y. So this line has slope, and I want to put slope in parentheses because we have to look at lines, slopes of lines, as something that's a two-dimensional figure. Line has slope. You know, we're in 3D, but we want to look at it from a two-dimensional point of view. Like the pitch of a roof, they call it pitch, but it's actually the slope of the roof, right? The roof is in 3 dimensions, but if you look at the cross-sectional cut, you kind of can imagine the two-dimensional picture of the slope. The road has a grade. That's also a slope. Go down to Half Moon Bay and Highway 94, 84, 94, whatever. It says there's a 6% grade going down. So that means the slope is 0.06, right? 6 over 100. So for every 100 feet that you move in a horizontal direction, you go down 6 feet. So the road is in 3-dimensional space, but we look at the slope as something that's in 2 dimensions. So the line has slope f sub y at a particular point, AB, where x is fixed. So x is fixed, and you're only going in the y direction. Okay? So that's a general picture of it. Later on, we're going to take a look at more pictures when we start analyzing this thing. Maybe we can do a virtual reality demo here. Anybody in the VR club? No? Was? Maybe we'll have it set up over here. Section 14.6 would be probably the best time to do the VR stuff. But that would it's kind of, I think that'll just be weird. It'd just be me walking around. And you're just watching me walking around. But I think you're able to see what I'm seeing. Only one eye. Well, you'll get to see what I'm seeing as I look at the different angles. So it's almost like drawing it on one of those programs and then just looking at it from different points of views. Get the feeling you guys don't want to do it. Yeah, they don't have it. The other guy, the old president, used to have it. I'll see if I can get John to buy it.
Yeah, because I get about $5, so like the whole class can pitch in like 10 cents.
All right, let's do a quick example just for computation's sake, and you'll see how really simple this is. So I want us to be comfortable with a lot of different notations, but this is really the easiest. So fx is going to be what? 2x, right? The y squared is constant, so that's gone. Fy, negative 2y. That's it. That's all there is to it. And you guys probably take derivatives better than you integrate. So I didn't mean to say it that way. What I meant to say is that you guys are probably really good experts at being able to derive competitive derivatives. Oh, comparatively. All right, let's see. So back in Calc 1, it turns out that you can make up any function, and taking the derivative is easy. But when you go to Calc 2, you can't just make up any function because there's certain things that you can't integrate. So we're in derivatives again, so I'm just going to make up stuff, and we should be able to do it. Are there any product rules here? Product rules? Yeah, so they're not, right? So I'll twist this notation up a little bit, and we'll use a partial notation with respect to x. What's our first term here? 3x squared. And then now y is a constant, remember. So you could treat it like a product rule if you just remember the derivative of y with respect to x is 0 because y is a constant. But you don't want to do that. Just pretend the 3 and the y are constants, and then you take the derivative of x squared, and then you'll multiply that with a 3 and the y. Yeah, you can pull it out. So you can imagine having pulled that out as 3y and then take the derivative of x squared. So 3y times 2x is 6xy. So if you want to think about it that way, separating it, that's fine. If you want to keep the y just hanging around over there, just remember that when you write your answer down, the y is still there. Now we have a sine y. What might look like a product rule is actually a constant times the function. So sine y is a constant. What do you do when you take the derivative of something with a constant? Just leave it there, right? And just take the derivative of the function itself. So sine y was just a constant. We'll leave it there. What's the derivative of sine y? Or cosine x. Well, the derivative of sine x is cosine x. Now, this one. xy. So the derivative of e to the something is e to the something times the derivative of the something. And the something is x times y. The derivative of x times y is y. So it just pops up like that. Okay? If you want. So the first one is 0. We could put 0 there or not. And then here, 3x squared, right? Because y is the variable, so the whole thing, including the x squared, is a constant. And now, sine x is a constant. The derivative of sine y is cosine y. And then, all right. I've officially dubbed you experts of taking partial derivatives. That's the easy part.
The lab's completely just one. It just doesn't match like this.
The derivatives? When they ask you to just take derivatives?
The way they ask it, they give you no explanation.
Oh.
He's like, well, this is a constant. What's it going to be? And everyone's just like, I don't know what that means.
Yeah. Might need to look at the book. It's not good either.
Like even looking at the book didn't do it step by step like the lab did. So the lab was like the steps were just kind of you didn't know what you were doing because it was so granular. Like how do you do addition? You're just like, what do you mean?
Yeah. Has anybody ever lived outside of California where it actually snowed? So, visited during the winter time? So, not here. All right. Windchill factor. So, when it's really cold outside, it has a specific temperature. And you go outside and you can feel that temperature. But when the wind blows, it feels a lot colder. So that idea is called the wind chill factor. And the wind chill factor is actually a complicated formula that somebody came up with, where you're feeling both the temperature, the regular temperature, and the wind at the same time. That makes it feel a lot colder than what it is. So, for example, let's call this let's call it C for wind chill. Let's call the wind velocity V, and then the temperature T. So let's say this is C is function of V and T, where C is the wind chill. V is the velocity of the wind. And T, temperature. And T is a temperature. So, for example, if I want to figure out what C of 20, comma 10 is, I can put this in some complicated formula if I knew the formula, but if we have a table, I would look at the table and say there's 20, velocity is 20, the temperature is 10, and so it looks like it would be negative 24 degrees. It would feel like it's negative 24 degrees Fahrenheit outside.
That's, oh, if Fahrenheit, the other table for homework is in Celsius. Which is
Oh.
and it's like, that's like going to kill you. Negative 24 C. Yeah, that's really cool.
So negative 24 degrees Fahrenheit, I mean, it's below zero, right? But I don't think it'll kill you.
That's like,
I mean,
that won't
if you go out there in a t-shirt, you'd probably not last very long. But if you, I mean, people have lived in these temperatures, and so they just cover their noses. Make sure you don't get frostbite in your nose sticking out of your face.
lose your nose.
Yeah, I'd say it's extreme. So the coldest I've been in is negative 17. The wind chill factor became negative 17. All right, let's see what we're going to do with this information. Wind speed, yeah. That they call it wind velocity. We'll call it wind speed. All right, so let's put some context into our partial derivatives. So we know what the wind chill factor is when the wind is blowing 20 miles per hour and it's 10 degrees outside. We know that it feels like negative 24 degrees Fahrenheit. So now let's figure out what this means. What does the partial of C with respect to, let's do V of 20 comma 10. So now, let's use, we've been using the word slope because that's our nice natural visual relationship with the derivative. But now let's take derivative in another context, in another application. When else do you find the derivative of something? When you want to find the rate of change. So really, this is just, you know, those Mad Libs, you just fill in the blanks, but you know, you got to fill it in with the right answer. The rate of change of something with respect to the something else. So what are the two somethings? The rate of change of what with respect to what? So the C is our wind chill with respect to V, the velocity. So the rate of change of wind chill with respect to, there's a 2 here, the wind velocity. I guess we got corrected, it should be speed, wind speed. But we're still going to keep V. V for speed. V for wind. So we have this piece of information. We're not going to find the exact velocity or the exact rate of change, but we can find an estimate for the rate of change, like how this is going to change. So what we're saying here is that if you go outside right now and it's 10 degrees outside and the wind is blowing 20 miles per hour and you're standing there freezing, right? And then all of a sudden the wind starts blowing a little faster, right? So you're going to get colder. The wind blows 20 miles per hour, and then all of a sudden now it starts to blow 25 miles per hour. So your temperature the way you're feeling it will change, right? So the question is, what is the rate of change of your temperature from standing there where it was blowing 20 miles per hour to now it's blowing 25 miles per hour? So the way to get that is to get an approximation. So the best we can do is estimate. So we'll estimate this. So the way we're going to estimate this is that we want the derivative with respect to V, and so the temperature will be fixed. Note, temperature is fixed because you're taking the derivative with respect to the other variable. So the temperature, which one is the temperature? Temperature is fixed. And then now we're going to look at the change in the wind speed. Well, according to our table, there's two possible ways of change. We could change in the positive direction, we can change in the negative direction. So we'll take a look at both of those and maybe find an average. Temperature is fixed, change is in the wind speed. So what we want to do is we want to look at the change in wind speed. We'll take a look at F, I guess we call it C. We'll take a look at C of (20,10) minus C of what's before 20? 15, 10. So we'll take a look at the change in the wind chill divided by the change in the velocity. So our velocity changed from 20 to 15. It's like the delta y over delta x. It's delta v or delta c over delta v. Yeah? I was looking at that. I was kind of working it out in my head, and I think it didn't matter because what we'll do is that since we're dividing by the change in the velocity anyways, it'll match the signs up. So we'll look at the change from 15 miles per hour to 20 miles per hour. And then we'll look at the change from 20 miles per hour to 25 miles per hour. So C of 25, 10 minus C of 20, 10 divided by the change in the wind velocity, which is 25 minus 20. Okay? All right, we can look at the table to find these values. It looks like C of 20, 10, and we know what that is. That's negative 24. (15, 10) negative, is this 18? This is 18, right? Yeah. Divided by 20 minus 15 is 5. So this turns out to be 6? No. Negative 6? (24) was C of 20, 10 is negative 24. And C of, what is it, 15, 10 is negative 18. And we're going to do the same thing except looking at C of 25 comma 10, which is negative 29, I think. So this is negative 29 minus negative 24 over 5, and is the bottom negative 2? No, it's positive, yeah. Okay, so hey, am I doing it right? Is this okay? So this is negative 5 over 5, which is negative 1. Negative. Yeah. All right. So what we could do is we could just find the average between these two things, add them, divide by 2, and then that would be a good estimate for the slope, or for the rate of change. So we're looking at the rate of change a little bit before, we'll look at the rate of change a little bit after, and then we find the average, and that would be a good average rate of change between the two. So average here, so negative 1.1. So you're standing there and it starts blowing and then the wind speed starts to increase. You can feel your wind speed changing to about negative 1.1 degrees. So you're going to drop about 1.1 degrees for every increase in the speed of the wind. And that makes sense. It gets colder. It's negative, right? It goes down. The slope is negative. So it seems like it's going to go down. Okay? So that's a quick application of our new partial derivative. We could do the same. You're standing in there and then the temperature goes up from 10 degrees to 15 degrees and we can feel how the rate will change as the temperature goes up. You can actually Google Windchill Factor. If my D would work. Windows. Wind. Chill. My C doesn't work. Chimes. I'm going to get a new computer sometime. Or yeah, oh, hey, just plug in the keyboard. Man. I got a keyboard here. The thing is, sometimes if I plug in the keyboard, then my pen, the tablet, doesn't work anymore. You guys want to donate a new computer? I'm game. I asked for formula, right? Windchill formula. Wikipedia. There it goes. Wind chill index. So V is the velocity, T is the temperature. It's 10 root V minus V plus 10.5 times 33 minus T. Oh, this is in meters per second and Celsius. And then, so just do the conversion from Celsius to Fahrenheit and then the meters to feet, and then you'd be all good. Whatever. Yeah.
The rate of change is decreasing. Is that something physical, or is it just like how we see light, for example? Low levels matter more than higher levels.
I think it's physical because you're feeling the actual temperature drop. I mean, we're talking about wind chill still, right? Yeah, so in terms of wind chill, you're physically feeling your temperature dropping, and so physically see it too. Yeah, so it's a physical thing. It's not abstract in our scenario.
Well, I mean, like, is it the same thing, like how we see lower amounts of light matter more? But it's not linear.
All right. So if you are interested in the wind chill factor, you know how to Google it. Next is implicit differentiation. So let's take a look at implicit differentiation. What? I'll stop my keyboard here. So just like whenever we're trying to learn new things in Calc 3, let's try to come back and look at the old thing in Calc 2 and see how that used to work. So back in Calc 2 or Calc 1, good thing I typed this, huh? Look at how I write implicit differentiation. No. Figured if I say it as I'm writing, it's all good. And then if I look at my notes later without the video, what the heck is that? Let's do a simple implicit differentiation example from Calc 1, which is x times y is equal to 1. I don't know if this is even simple. Maybe this isn't that simple. This is too hard. Let's do an x plus y. No, let's stick with this one. Now, in implicit differentiation, what you need to do is, what you need to think about is we have to assume that y is a function of x. And so we don't do this in implicit differentiation, because if we do, then it would be way too easy. But if you wrote this as x times f of x instead of x times y, then this whole idea of taking the derivative of this will seem really, really easy, I think. So if I take the derivative of this, and by that I'll say d dt or d dx, notice the regular d, right? So the d dx of this is taking the derivative of this with respect to x. Derivative of the first times the second plus the first times the derivative of the second. And this is the part that not everybody, a lot of people make a mistake on back in Calc 1, is that the derivative of 1 is not 1, it's 0. It's just a common mistake. And so you're looking for y prime, which is essentially f prime. And so you just do some algebra. This is another step in implicit differentiation that's really kind of difficult for a lot of people, is solving for your f prime. So since we're all in Calc 3 now, I'll do this in one step. Let's see if I can do it correctly. So bring the f of x over to the other side. That would be a negative, and then divide by x. So this is how easy it would be if you just assume that y is equal to f of x, which is what implicit differentiation is asking you to do. It's asking you to say that one of the variables is an implicit function. It's a function of the other variable. Now, if I were to do this using the regular implicit differentiation, if you remember the rules, you treat y as a function of x. So derivative of the first times the second plus the first times the derivative of the second, and then you solve for y prime, which is the same thing, except if you're used to that idea that y is a function of x, then you're ready to tackle more complicated equations that have multiple y's in it, which is what sometimes happens. That's the idea behind implicit differentiation way back when. So way back now, if you have a relation between the x, y, and z, and somebody tells you, oh, by the way, z is a function of x and y, then you want to find the derivative of z with respect to x, for example. So in our assumption back then, we made the assumption that y is a function of x. In this case, we have to make the assumption that z is a function of x and y. And so when you take derivatives, you're taking partials. So if you want to now take the derivative of this, you have to take the derivative with respect to x. It's d dx. Oh, but my d is now partial d. Right? As opposed to the straight d. Partial d. I want to take the derivative of this expression with respect to x. So I have to look at this. X is a variable. Y is a constant. And z is your function. So let's just ignore the y because it's a constant. And then we have x times z. Taking the derivative of that, we have to use a product rule. So x, the derivative of x, derivative of the first times the second plus the first times the derivative of the second. So there's our product rule. Well, I didn't replace it. I took the derivative of z with respect to x. Equals 1? Equals 0. So dz dx is equal to negative yz divided by x y. I guess that can cancel negative z over x. Do you know why we do implicit differentiation? So let's see if we could take this example, y is equal to, or x times y is equal to 1 in 2 dimensions first. So it turns out that if you have a relation between x and y, it may or may not be a function. In this case, it just happens to be a function. But there's a possibility that it's not a function. A better example probably would have been, this is what I wanted to change my mind to, but I decided to stick with the xy. So x squared plus y squared is equal to 1. We know that that's a circle. Is a relationship between x and y that doesn't give you a function. That's not y is a function of x. Right? But we can still study its derivatives, its slopes of the tangent lines. Right? And we can still see slopes there all over the place if we wanted to. So the idea is that if we can write y as a function of x, then that would be great. Now, the unfortunate thing about this is that if you solve for y, see if I can solve for y. No, I can't. If you solve for y, you're going to get a couple of if you solve for y, you can force to make this look like a function by just taking half of it, which means you lose the other half. So y can certainly be explicitly written as a function of x, but then you might not get the whole picture. But for some people, that's okay. At least we can now take the derivative and then be able to work with that. So that's the same idea with something like this. Explicitly, it might not be a function, although in this case it is. So explicitly, it might not look like a function, but if we take just a piece of it, we can write z as a function of x and y, and then treat it like it was a regular function going from R2 to R. So what we just found is the generic derivative of this thing going in the direction of x. Okay? All right, so I think that's it for today. Implicit differentiation. So this particular section has a few more things to discuss, some higher order derivatives, and then taking a look at the relationship between derivatives and level curves. So we'll do that next time.